N-MOSFET fabrication flow. By Group 3. 1. Wafer preparation. We start by cutting a thin wafer from a single crystal of pure silicon. This wafer serves as the foundation for our transistor. 2. Doping. During crystal growth, the wafer is doped with p-type impurities such as boron to create the desired electrical properties. 3. Oxidation. A thick silicon dioxide layer, about 1 micrometer thick, is grown over the wafer surface to act as an insulator and protect the wafer during subsequent processes. 4. Lithography. The entire surface of the silicon dioxide layer is coated with a light-sensitive material called photoresist, which helps in patterning the wafer, and spinning the wafer allows to achieve uniform distribution of the required thickness. 5. Exposing to UV radiation through mask. This photoresist layer, which is sensitive to light, is then exposed to ultraviolet light through a mask that defines the regions where diffusion is to take place, along with the transistor channels. The areas shielded by the mask remain unaffected, while the regions exposed to the ultraviolet radiation are polymerized or hardened. 6. Etching. The soft, unpolymerized photoresist and the underlying silicon dioxide are etched away, exposing the silicon wafer in the defined areas. The exposed silicon wafer surfaces are now ready for the next steps in the process, as defined by the mask. Any remaining photoresist is stripped away using hot sulfuric acid, leaving a clean wafer surface. 7. Thin oxide growth. A thin silicon dioxide layer, approximately 0.1 micrometer thick, is grown over the wafer to form the gate oxide of the NMOS transistor. 8. Coating with polysilicon to form gate. A layer of heavily doped polysilicon is deposited on top of this thin oxide using the chemical vapor deposition technique. 9. Coat with photoresist. After the deposition of the polysilicon, a layer of photoresist is coated on top of it. 10. Exposing to UV radiation through mask. A mask defining the gate is placed over the photoresist and exposed to UV radiation. 11. Etching. As a result, the polysilicon over the portion excluding the gate region is removed, and the polymerized photoresist is also stripped away. 12. Diffusion. The exposed thin oxide is now removed to clear the regions where the N-type impurities will be diffused to form the source and drain. This diffusion is achieved by heating the wafer to high temperatures and passing a gas containing the required impurities, such as phosphorus, over the surface. It is important to note that the polysilicon over the gate oxide and the thick oxide over the other regions act as masks, preventing diffusion in these areas. This is known as the self-aligned process. 13. Oxide layer growth. The entire wafer is covered with another thick silicon dioxide layer. This layer will later be patterned to create electrical contacts. 14. Exposing to UV radiation through mask. A mask and photoresist are used to define the regions where electrical contact source, gate, and drain will be made. 15. Etching. The silicon dioxide is etched away in the defined regions, exposing the areas where the electrical contacts will be formed. 16. Selection of areas for contact cut. The remaining photoresist is also stripped away. 17. Metallization. Aluminum is deposited over the entire wafer to a thickness of 1 micrometer. This metal layer will form the electrical connections. 18. Coat with the photoresist. This metal layer is masked and etched by coating it with photoresist. 19. Exposing to UV radiation through mask. Exposing it to UV radiation to form the required electrical connections. 20. Etching. Etched using photoresist and UV light to create the required electrical connections. 21. Final NMOS transistor. This is the final NMOS transistor that is fabricated on a p-type substrate into which two heavily doped N+ regions are diffused. These N+ regions act as the source and drain terminals of the NMOS transistor. The device is now ready for integration into electronic circuits.